All right, good morning. We are getting ready to start Chapter 7 today. So we're trying this video thing, and we're going to see how it works. I apologize if it's bad, but if it doesn't work, then on Tuesday when I come back, we will jump in and catch back up again and move on from there. So let's see what happens as we do this. So get out your Chapter 7 notes packet. You should have had it. It's at the front of the classroom. If not, take a minute and go get that right now. If you need to hit pause on your video, hit pause and then come back to it and get your 7 notes and get ready to go. So I'll pause for just a second and then we'll pick back up again. You should have your Chapter 7 notes in front of you now. And so a couple things on here, a couple of dates that I want you guys to write in here. First of all, the 7-1 quiz will be on January 23rd. So January 23rd for the quiz for 7-1. The 7-2 quiz is going to be on January 28th. And the 7-3 quiz is going to be on January 30th or 31st for block day, depending on what odd or even there. And then our Chapter 7 test is scheduled for February 5th and 6th. That is a Tuesday and Wednesday before parent-teacher conferences. We'll do the multiple choice on one day and the free response on another day on that February 5th and 6th. So hopefully you have those dates down, and let's jump in and talk about what a sampling distribution is. Now, at the top of your notes here, I want you guys to highlight, circle, underline this ing, a sampling. I'm going to emphasize that over and over and over and over again. A sampling distribution. You have to know the difference between a sample distribution and a sampling distribution. So, kind of give you an idea of what we're talking about here. A sample is a group of individuals that you're going to gather information about. And what you would do is, like if you're gathering ACT data, you would plot each individual's ACT score. That's a sample distribution. A sampling distribution is where you go to every single classroom in the school and ask everybody in the class what their ACT score is, and you average all of them and you record that data. The average ACT from classroom 1, the average ACT from classroom 2, the average ACT from classroom 3. Then you plot all of those averages. That is a sampling distribution. So a sampling distribution graphs a collection of statistics. Not a collection of individual values, but a collection of statistics. So it's really important you guys understand this first box on here, difference between a parameter and a statistic. A parameter is a value from a population. A value from a population. So, like, for example, in the example we were just talking about, the parameter would be the mean ACT of every student, all of them, the mean of all students at Olathe Northwest High School. That is a parameter. Usually it's unknown. A statistic is a value gathered from a sample. They're two different things. Got to know the difference between a population and a sample, know the difference between a parameter and a statistic. The nice thing is parameter, P, goes with population, P. Statistic, S, goes with sample, S. The difference between a population and a sample, we just talked about that. A population is everybody in an entire group that you're trying to gather information about. The sample is just a representative group from your population that you're going to use to estimate with. Notation-wise here, there's a lot of things here that's really important. So you have to know the difference between the population mean, the population standard deviation. Sample means sample standard deviation. All of these things, all of these notations are going to be really important. So I'm going to pause the video and I'm going to write these in, and I want you guys to copy them down. So population mean is mu. Sample mean is x bar. Population standard deviation is that sigma. Not very good, but I'm trying to draw with the mouse. Sample standard deviation is S sub x. Population proportions. We're going to be talking about proportions in this chapter and moving forward. So you have to know the difference between a population proportion, the percentage of all students, which is just P, versus the percentage of students from a sample, like the percentage of students from our class. So we use a hat to represent a sample proportion, or P hat. That should look familiar going back to chapter 3 with Y versus Y hat. The Y hat was an estimated value. So here, P hat is an estimated proportion. We're using a sample to estimate the population. So P versus P hat. Population total. The total number of people in the population is a capital N, and the sample total would be a lowercase n. So in our example, capital N would be the 2,100 students at Olathe Northwest High School. The lowercase n, the sample value, the number in the sample, would be the number of students in our class. Okay, so it is really important to know the difference between all of these notations. Notation is huge. You've got to know the difference and use the correct notation. You're going to lose points. You're going to get really confused. So make sure you have those copied down right. Get in the habit now of using correct notation. So let's practice this. I want you guys to read this and identify the population and the parameter. Identify the sample, the statistic, and use the correct notation. So we're looking at the bold-faced numbers. Is this a parameter or a statistic? Is this a parameter or a statistic? So on question A, bottles of Arizona iced tea are supposed to contain an average of 20 ounces of iced tea. Quality control people came in, they inspected sample of 50 bottles, and they measured those, and they contained 19.6 ounces of tea. So which one is a parameter? Which one is a statistic? You should have said that the mean, the mu of the population, is the 20. That is what it should be. That is what the population value should be. And the sample statistic should be 19.6. Okay, try letter B on your own real quick. And again, as we're going through these, if at any point you need to hit pause because I moved too quickly, hit pause, do what you're supposed to do, come back and hit resume or hit play again and keep on going. Again, I want to remind you guys at this point, like as we're doing this, you only learn if you do it and then check. If you're just waiting for me to write it down on the screen and copying it down onto your notes, you're not really engaging very well. You're not going to learn as much as if you actually do it yourself and then watch what I write down to check yours and then correct it if you need to. So if I give you time to do it, I want you to take the time to do it so that you can learn the most and retain the most from this. For letter B, we're talking about a New York to Denver flight. 8% of the passengers were selected for screening. Supposedly TSA is supposed to screen 10% of all passengers at the airport. So which one is the population and which one is the sample? In this case, the 8% is my sample proportion. The 10% is my population proportion. So my population proportion, P, should be the 10%. My sample proportion, P hat, is the 8%. And just to connect an idea that we talked about before, what would the 125 be? That is my sample, lowercase n, my sample count. We selected 125 passengers to sample that with, so that is my sample count. Okay, more practice with this. For the sake of time and everything else, I'm not necessarily going to go through this. If you're lost or struggling with this, you can come in and we can go through some of these other examples here together. For sake of time, I want to get into the meat of 7.1. What is sampling variability? Well, what is variability? We know that variability is going to happen in it's inevitable. Sampling variability is the known variability from one sample to the next. So, if I take a sample of 10 students and ask them their mean ACT score, or ask them their ACT score and find the mean. And then I go get another sample of 10 students, and another sample of 10 students, and another sample, and another sample, and another sample. I know that there's going to be variability between my first 10 to my second 10 to my third 10 to my fourth 10. That is sampling variability. We know it's going to happen. What's our goal with variability? Going clear back to chapter 1. What's our goal with variability? You may want to write this in here. We want to minimize variability as much as we can. So we want to minimize that variability from one sample to the next as much as we possibly can. That is done by taking a good sample. The bigger the sample is, the less variability there is, because those outliers don't have as big of an impact. If I sample 2 people, if one of them has a really low ACT score, my average is going to be really low. But if I sample 10 people and one of them has a low ACT score, that one low ACT score is going to be balanced out by the other 9. If I sample 100 people and one of them has a low ACT score, that one low ACT score is going to be way more balanced out for the rest of the 100 or the other 99. And so that outlier, that one low ACT score, that one high ACT score is going to be balanced out. So the bigger the sample is, the lower the variability is. That's kind of a key idea as we go throughout all of this. A sampling distribution is a distribution of really all samples of size n from a population. So, sampling distribution, going back to that ACT score. If we're going to sample 30 students and ask them their ACT score and plot their mean ACT score, what's going to happen is in order to do a true sampling distribution, theoretically, I have to ask every single possible different group of 30 students. So there's 30 of you in here, say that for example. That's one group of 30. Now, take one of you out and put a different student in. Now that's a different group of 30. I have to ask that group of 30, and then take another one out and put a different one in, so on and so forth. There are billions upon trillions of different sample sizes of 30 out of a group of 2,100. So that's why I said it's theoretical. We can't really ever ask every single possible sample out of a distribution when we're talking about large numbers. Now, you're going to do a couple of practice problems with this where you do practice doing every single possible sample out of a group. And so that is possible if it's a small population and you're working with different sample size, fairly large sample size. But in big populations where most statistics is most often used, you can't actually do this, so we do it theoretically, which is what this chapter is all about, the theoretical building of a sampling distribution. There it is again. I'm going to emphasize that "ing." Sampling distribution. It is a collection of different samples data. So, for example, here. A father has 4 sons of height 68, 71, 72, 75. Determine the sampling distribution of the sample mean height for samples of size 2. So what's going to happen? You're going to take every single possible group of 2 out of this father's sons. He has 4 of them. Every single group of 2, and you're going to find the mean height. So, putting this together and doing it. My first sample is going to be 68 and 71. My next one that I can do would be 68 and 72. My next one that I can do would be 68 and 75. Eventually I'll get to where I have a stylus to be able to do this and it'll be a little bit cleaner. Apologize for now. My next sample of size 2 is going to be a 71 and a 72. My next one is going to be a 71 and a 75. And then my last one is going to be a 72 and a 75. Find the mean for all these. Okay, so you should be coming up with means of 69.5, 70, 71.5, 71.5, 73, and the last one over here was 73.5. So now, if we were to graph all of these, my lowest one was 69.5, so if we go 69, 70, 71, 72, 73, and 74, and make a dot plot of these. By the way, this is what you should have done yesterday with your German tank simulation for your 15 samples. It's done this 15 times, found all 15 of these and made a dot plot. Your dot plot for this particular example would look like this. We have a dot there at 69.5, a dot at 70, 2 dots at 71.5, a dot at 73, and a dot at 73.5. So make those a little bit bigger here so we can see those values. So there's my dot plot for it. Now, how well did this actually do at predicting the true population mean? So now I want you to actually find the population mean. I'm going to let you think about this for a second. What am I asking you to find when I ask you to find the population mean? Okay, the population mean should be 71.5. If you didn't get that, the population mean would be the mean of all four numbers. The true mean of all four values is 71.5. So, this is my sampling distribution. I took 5, 7, 6 different samples from this, graphed all 6 samples of size 2 on my dot plot. This is my sampling distribution. And what we're getting to, and we're going to be measuring here in just a minute, is how well did this sampling distribution represent my true mean? Well, let's go to my sampling distribution and kind of putting together some ideas here. The shape of this should be roughly symmetric. Where's the center of that distribution? It should be at 71.5. So, did this sampling distribution do a pretty good job of estimating my population mean? And it did. So that's what the goal or the purpose of a sampling distribution is to try to take as many samples as we can and use it to try to estimate or represent the true population. Because in reality, most of the time, we won't know the true population value, and so we're trying to estimate it based off of a bunch of samples. That's what we'll get to a little bit more theoretical understanding a little bit later. Okay, so we're just going to kind of talk through this a little bit. We're not necessarily going to do all this. I'm going to breeze through this pretty quickly. Mars says that a bag of M&Ms has 24% blue, 20% orange, 60% green, 16% yellow, 13% red, 13% brown. Assume it's true. We want to examine a proportion of orange in a repeated sample of 50 candies. So population distribution would be graphing 24%, 20, 16, 13, 14, 13, and 13 on a graph. Probably be a histogram. Since this is a categorical, we'd make a histogram with that. Individuals would be the M&Ms. The variable would be color. The parameter of interest would be proportion of orange M&Ms. So if we were going to represent that, what we are trying to estimate here is P is the true proportion of orange. kind of something that will lead you to what we'll get to later on as well. You'll have to identify the parameter of interest. Okay, so then on part B, it now says, imagine taking a sample of 50 M&Ms, make a graph showing the possible distribution of your samples. So if you're going to do this, you're going to imagine drawing a sample of 50 M&Ms, and you're going to estimate or make up the percentage of them that are of the various colors, and you're going to make a sample distribution. So let's say that I had 20% that were blue. I had 18%. Now remember, this is out of my 50 that I'm making up. I'm just making these numbers up. 18% of them that were green, so on and so forth. Okay, so this is a sample distribution. The sample distribution should look very similar to your population distribution up here. Now, will it be exactly the same values? No, because you're going to get sampling variability. So you're not going to get exactly 24%, 20 orange, 16 green in your sample that you make up or that you actually do. You're going to have some variability to it, but that is a sample distribution. Now, keep in mind, what are we trying to estimate? What's our parameter of interest? We're trying to estimate the proportion that are orange. So let's say we down here on this sample distribution over here at orange, you ended up with 12% of your made up distribution that was orange. Okay, so this is what we're trying to measure. Okay, so now it's asking which of these would be an appropriate sampling distribution describing our statistic. What's our statistic again? It is we're trying to estimate the proportion that are orange. Well, we'll go back up here to our population. 20% of my M&Ms from Mars say they're supposed to be orange. So which one of these shows that a sample proportion should be around 20%? And it should be, well, here, let's do this again. Should be this one right here. Notice it is centered at 20%. And it has the p hat. Because p hat is my sample proportion that was orange. Okay, population proportion, sample proportion, sampling distribution. Key to know the difference between them. Now, our goal with these sampling distributions, we want to try to see how well they do at estimating the true population value. Finishing this up here, I've gone too long already. I want to finish this up pretty quickly, and this is where we'll pick up on Tuesday. An unbiased estimator should be centered at the true population value. A biased estimator means that my sample did not predict my population very well. There was bias in it. So a biased estimator does not accurately represent the population parameter. Unbiased is centered at the population parameter. Biased is not centered at the population parameter. What's the variability of a statistic? The variability is how spread out that sampling distribution is again. Again, we want low variability. The best way to reduce variability is to increase your sample size. So, I want to show you an idea of this biased versus unbiased estimator here real quickly, and then this is where we'll stop. So imagine that these bullseyes are your graph, your sampling distribution. The center of the bullseye is the population proportion. Okay, so this particular one has very low variability. All the dots are grouped together, but it's biased because my grouping was not centered at the population value. So this is a biased estimator, but it has low variability. This one is an unbiased estimator because it is relatively centered around the bullseye. That graph, if we were to graph it, is going to be centered around the bullseye. However, it has fairly high variability because the dots are pretty spread out. I didn't do a very good job of hitting right in the middle, so it's pretty spread out. This one has high bias because it's not centered very well, and it has high variability. The dots are spread out. So our goal is to have low bias, low variability, centered at the right value, along with low spread. We want that distribution to be fairly narrow around the true population parameter. So this is an example from our German tank simulation. All of these are centered fairly closely at the true population value. This one has the most variability. This one has the least variability. But they're all centered fairly close to the true population parameter, true number of tanks. So they all have low bias. This one probably has the most bias because the center of this distribution is skewed over here. So this one is skewed left. The center is over here, so it's not focused on the true value. So this one has the lowest, or excuse me, the highest bias. It also has fairly low variability compared to the other ones, but it has high bias, so it's not a very good estimator. The one that they actually used was this one down here because it had fairly low bias and fairly low variability as well. So kind of give you an idea with that. From here, what I want you guys to do is get out your practice problems that you should have. If not, they're up at the front of the room. The sub has them, and begin working on those practice problems for 7.1, and we will pick up from there on Tuesday. Have a great weekend.